Okay, we come to this elastic and plastic behavior of this particular cross section, and we are analyzing this cross section by elastically and plastic behavior. So we have seen this here. Just a minute. We have seen this in elastic behavior, that is compressive force is equal to tensile force, and my how to calculate, and what is my and ZE. So my is the yield moment and ZE is the elastic section modulus. Now in the again same in the plastic condition. So again compressive force is equal to tensile force. So this compressive force, the area in compression is equal to sigma y into AT. Area in compression means stress in at yield into stress at correct stress at yield into area in tension is equal to area in compression. Similarly, we have seen this formula in the design of steel structure and introduction to plastic and plastic analysis of beams and portal frame. So stress into area at compression plus area at tension into centroidal distance. So this formula we have seen. So by using this, we can calculate the plastic moment. So here we have calculated the elastic moment, and in the plastic zone we have to calculate plastic moment. That plastic moment is calculated by again sigma y into ZP. So here ZP is the ZP is the plastic section modulus and MP is the plastic moment. Similarly, in the elastic, My is the yield moment, MP is the plastic moment, ZD is the elastic section modulus, ZP is the plastic section modulus. So by using this behavior of material, it means stress and strain, we have to calculate moment, that is yield moment and plastic moment for the by using the elastic section modulus and plastic section modulus. So this is the analysis. So now if we see if you see we can take the example of the rectangular section. Now we have taken the example of irregular shape. Now we will take the example of rectangular cross section. So if we see here, this is the rectangular cross section. This is the rectangular cross section. B is the width, D is the depth of this section, and here CG. So CG at center, it means at D/2 distance from top and D/2 distance from bottom. So this is the D/2 and D/2. So now elastic behavior. See first elastic behavior of section. So elastic behavior of section means this is the area in compression and this is the area in tension, and the variation is linear. This is the linear variation. Why elastic? Because in the elastic behavior, stress is directly proportional to strain, and here the stress is increasing. You can see here stress is increasing and stress is preferably constant or less. Strain is preferably constant or less. So strain is increasing. It means the linear variation is shown here. Now in the elastoplastic behavior, same. In the elastoplastic behavior, stress is constant. So that's why here this much part is a constant from the top and bottom also. So here again compressive, this is the compressive zone and this is the tensile zone. So in the sum of the elastoplastic, so in this area, whatever this linear line is there, this is elasto and other part is a plastic. So this is elastoplastic zone, and last is the plastic zone. Here stress is constant and there is a no elasticity, only elongation of increasing strain is there. So here this is the behavior of this is the behavior of your member. So here compression zone is there and tension zone is there and no elasticity is there. So this is the your behavior of the rectangular cross section. Now we have to do the analysis by considering the elastic behavior and by considering the plastic behavior. So here if you see if we see here the first elastic behavior. So as we have seen in the last slide, there is one cross section is there, My and Ze, and MP and Zp value we have calculated by the formula we have seen in this last slide. Now again Ze, here in the elastic behavior, Ze and My we have to calculate it. So My is nothing but sigma y into Ze, and Ze. So now Ze, how to calculate Ze? So Ze we can calculate by using Ze is equal to I by Y. So initially we have to calculate the moment of inertia of this particular rectangular section. So moment of inertia of rectangular section I is equal to BD cube by 12. We know BD cube by 12 is the moment of inertia. So BD cube by 12 divided by Y here. Y is the depth. So Y is the D by 2. So if we do this calculation I by Y, we will get Ze value. This Ze value is a BD square by 6. So Ze we got stress. Again, what is stress? P by A. That also we will get stress, and by using this formula we can calculate the yield movement, that is My, in the elastic behavior. By considering the elastic behavior, we can calculate this My, movement at yield. So this is again C is equal to T, means compressive force is equal to tensile force, and by using this formula, this is the final our calculation. Whatever I told here, I by Y. So here BD by 6. So again BD by 4 into 2/3. So we will got this BD square by 6. Ze is equal to BD square by 6, and we will got this My value. So now we have to see the plastic behavior of this rectangular section. So again, so in the plastic behavior, there are we can see the elastoplastic behavior. So in the elastoplastic behavior, there are two different sections are behavior is there. One behavior is the plastic behavior. This is the plastic behavior, and another triangle is the elastic behavior. Again here in the tension also, this behavior is the elastic behavior, and this behavior is the plastic behavior. So elastoplastic, some of amount elastic behavior is there, in some area plastic behavior. So here C1 T1 and C2 T2, there are two compressive force are there and two tensile forces are there. And for this again sigma y into Z, this sigma y into Ze. So we can derive this formula here by this formula, and we can calculate here MEP and MEP, means moment, plastic moment for this C1 force and plastic moment for this C2 force. Similarly, plastic moment for this T1 and T2, because C1 is equal to T1 and C2 is equal to T2. So if we calculate for C1, MP for C1, it will be same for T1, and if we calculate the MP for C2, it will be same for T2. So this is the elastoplastic behavior. And we can calculate this MP. So now fully plastic behavior. Plastic behavior. Elastic behavior we have seen, elastoplastic behavior we have seen, and now here we have to see the plastic behavior. Fully plastic behavior. This here strain is a constant. So now C is equal to T. Again, compressive force is equal to tensile force. So now MP is equal to again sigma y into ZP that we have seen in the last two slides. So MP is equal to sigma y into ZP. So ZP we have to calculate now. So for calculation of ZP, so we have used the formula where ZP is equal to BD square by 4 for the rectangular section. How to calculate ZP? ZP is equal to sigma y into area in compression into x bar 1 into area in tension into x bar 2. So by using this formula, we can calculate the ZP. So now here ZP calculated. So by after the calculation of ZP, we can after calculation of ZP, we can calculate the MP. So MP is equal to what? Here written, we have written MP is equal to sigma y into ZP, and My is equal to what? Sigma y into ZE. So Z after calculation of ZE, we can calculate My, and after calculation of ZP, we can calculate MP. So My and MP, these are the two moments, elastic moment and plastic moment we can calculate for this rectangular section. So here next point is the shape factor. So what is shape factor? So shape factor is nothing but it is the ratio of elastic to plastic moment capacity. It means elastic moment, it is the ratio of elastic moment to the plastic moment. So here this F is equal to shape factor. So S is equal to elastic. So MP by My. It is the ratio of plastic moment to the elastic moment. So MP by My. So sigma y into ZP is MP and sigma y into ZE is a My. So ZP upon ZY is the shape factor. So shape factor S or F is equal to what? ZP upon ZE. So ZP. So ZP we can calculate it by using formula that is the BD square by 4 is a ZP and BD square by 6 is a ZE. So here by calculation we will got the shape factor for the rectangular cross section is a 1.5. So S is equal to 1.5 is the shape factor of a rectangle. And by using this shape factor, we can calculate the moment, plastic moment and yield moment. Again, by using shape factor, we can calculate the collapse load or collapse moment. So now, similarly, here we have taken the example of the rectangular section and we have calculated the shape factor. Similarly, we can calculate the shape factor for this particular area. Plates, we can calculate the shape factor for I section, the shape factor for I section. These are the standard values. Shape factor for I section is 1.12 to 1.15. Shape factor for hollow circular is 1.27. Shape factor for rectangle is 1.5. Shape factor for circular section is 1.698. Shape factor for T section is 1.8 and shape factor for diamond section is a 2. So these are the shape factors for the particular sections. We can using the behavior. We can calculate the considering the behavior of the cross section under the elastic, elastoplastic, and plastic condition. So we have covered the basics of plastic analysis part in this particular today's lecture. So we will stop here today. So this much part we have analyzed for the and we will help for the to learn the behavior of the member when member under the loading condition. So this so we will stop here today. We will see the next part in the next class.